Hello. In this video, we'll talk about the empirical assignment for Chapter 15. I'm going to do as I've done in the past and use a different data set with different variables to go through the same problems that you have to do in your homework problem. So the program starts off here with just the usual thing, clears things and closes the old log file, opens a new one, makes sure there's no pagination so you don't have to hit more to see all of the output and so on. Reads in the data. Your data set will be different, of course. So what my data set will have in it is two variables, which are going to be the personal consumption expenditures index, which is a measure of the consumer price index. It's a different way to measure inflation. It's the one the Fed usually uses. So I'm going to use that rather than the CPI. And on the left-hand side, I'll have wages. And so I'm going to regress wages, as you can see here, on the current and the lagged value of this consumer price index, the PCE, the personal consumption expenditures index, as it's called. And so I want to see how changes in these prices affect wages. And we'll come back to that in a minute. And so your data set's going to be a little bit different. It's going to involve two variables, real GDP and the federal funds rate. My data set starts in 1965, as you can see here. Yours starts in 1954. Mine's going to end in 2017. Yours will too. But I'm going to have you stop your sample at 2007 Q4, so you'll need to change this keep command. But anyway, let's start going through this program to see what you need to do on your homework. And so, as I said, this just does the usual things and brings in the data. This is what we learned last time. These three commands, what they're doing is setting up a date variable. There's already a date variable on your data set, but the program can't read that. And so we have to set up a new one. And when it reads it in, it'll set it up as a new column over here, column D, if you were to look at the data. And so anyway, so this just generates that date variable. And again, you'll need to change the date here, but the rest should be pretty much the same. You'll need to change this keep statement to get your data set right. Yours will end at 2007 Q4 and start, I think, in 1954. The problem will let you know for sure. And so the first part of this problem, again, the chapter is divided into two main cases. One where we assume exogeneity of the right-hand side variables, and so they're uncorrelated with the current and past errors. And the other is where we assume strict exogeneity, and that's where the error term is uncorrelated, not only with the current and past value of the error terms, but also future values. When we have strict exogeneity, we're able to use a different and more efficient estimation technique. But if we just assume exogeneity, then the way that we estimate the model, now this model is assumed to be wages as a function of some constant beta 0 plus beta 1 times PCE plus beta 2 times the lag of PCE and so on, up to beta 6 times the 6 lag of PCE. And so we're regressing wages on PCE and 6 lags. I guess this would be beta 1, beta 2, beta 3, there'd be 7 betas because we have the current value here, and there's also a beta 0 for the constant. So there'd be 7 betas in this example. Okay, so when we have strict exogeneity, what we have to do is just estimate this by OLS. So we use the reg command. And then we use robust standard errors. What we're assuming here is the errors in this problem are autocorrelated, first order autocorrelated. So UT equals rho UT minus 1 plus an error term. And that error term has all the nice properties. But the UT equals rho UT minus 1 gives us autocorrelation. What this comma R does, of course, is correct for either heteroscedasticity or autocorrelation problems, so it gives us robust standard error. So with exogeneity, that's all there is to estimating this model. Now, for the next problem, we'll want to save the residuals from this regression. So we're saving them in a variable called u. And then If you remember, the coefficient on PCE here is what we call the impact multiplier. It's the effect of a change in PCE on wages in the current time period. If we wanted to know what's the effect after 3 periods, we'd add up the coefficients on these terms up to the third lag, and that's what this gives us here. And then finally, what we call the cumulative or the long run multiplier would be the sum of those 7 betas from beta 1 on PCE, beta 2, 3, 4, 5, 6, 7 up to L6. And that would give us the value of what we call the cumulative multiplier. So let me run this and show you what happens. Scroll back to the top. So here's that first regression. This is the contemporaneous value of PCE. Wages is the dependent variable. These are the lags. This 0.5745 rounded is the impact multiplier. If we added these up through the minus 1.967 here, that would be we added all those, that'd be the impact, that'd be the effect of a change in PCE on wages through 3 time periods. And if we want to know the long run, we'd add all these up. And that's what this command does here. Display underscore B PCE gives us the impact. Display the sum gives me the effect after 3 periods is 0.4312. The impact was 0.574, and so on. And here's the total multiplier, which just adds up all 7 of the coefficients. Okay, next comes problem 2. So that was problem 1. In problem 2, what we want to do is assume strict exogeneity. And so that allows us to use this procedure called generalized least squares. And in general, what generalized least squares is a way of taking the model that has some problem, heteroscedasticity, autocorrelation, whatever it might be, and you find a way to transform that model that makes the error terms have the properties that you want, be homoscedastic and independent and all those sorts of things, those assumptions that we've talked about all through the course and in 320 as well, for that matter. And so it's a way of transforming the model. Now what you do with autocorrelation, the problem is ut equals rho ut minus 1 plus an error plus et, let's say. So ut is rho ut minus 1 plus et. We want to isolate that et. So if we take some quasi difference ut minus rho ut minus 1, that would equal et. And that's what this transformation is doing. It's transforming the model in a way that isolates just that et term. So to do that, we need an estimate of rho before we could get the quasi differences. And that's why we save these residuals, the estimated errors, the u-hats. And so the first step in the one-step GLS procedure, we'll come to the multi-step or the Cochran-Orcutt procedure shortly, is just, as it says here in the comment, to use the residuals to regress ut on ut minus 1. And that's what this does here. And then we save the value of rho, because I'm going to use that later. So I called this rho 0. That's my first estimate of rho. When we iterate, we'll have more than one estimate. And then I just displayed it so I'd have it. One of your questions asks what rho is in this problem, in problem 2. And so that's here. Then you remember for the one-step GLS, what we do is we quasi-difference the data and then run a regression on the quasi-difference data. And so that's what these commands do here. This comment here talks about this a little bit, exactly what's going on with the quasi-differences. We're just taking the left-hand side variable and subtracting off rho, the rho we estimated up here, times yt minus 1, that's the quasi-difference. And we do the same for all the right-hand side variables, xt minus rho hat times xt minus 1. And that's what these two commands do. They generate those quasi-differences. Okay. Then we run the quasi-difference regression, and that's what this command is here. It's just the QD means quasi-difference, of course. So it's just the quasi-difference wages on the current and those 6 lag values. Now, one thing important here is that after quasi-differencing, the coefficients on these x's, this B1, B2, B3, 4, 5, 6, 7, the betas, those are all still just betas. And so the estimates of these give us estimates of beta 1 through beta 7, beta 1 hat through beta 7 hat. But the constant is not beta naught hat. The constant is beta naught times 1 minus rho. And that's going to come into play in just a minute. Okay, so we run this regression. That's the one step. We only quasi-difference once. That's one step. We just got one estimate of rho, one step. And from this equation, the coefficient on the contemporaneous value, the time t value, is the impact multiplier. And then we add up all of the current contemporaneous plus the 6 lags, like here, we get the long run multiplier. And the question asks you about those. Okay, so that's really all there is to the first 2 of the 3 problems. In problem 3, once again, we assume strict exogeneity, but now we want to use something called iterative GLS. Statistically, one step gives you all the nice properties that you need, but iterating seems to help, so a lot of people go ahead and they use this iterative GLS procedure. So what we're going to do is we're going to estimate rho again and again in this iterative procedure until the value of rho doesn't change by very much. And for your problem, I made it so that the absolute value of rho doesn't change by more than 0.001. Oh, I actually forgot to show you the estimates for these quasi-difference regressions, but that's this GLS one step. Here's the estimate where we, this is for problem 2, where we estimated U on its lag. The correlation coefficient, the rho, was 0.9275 rounded. It prints out here, as we said. And then we generated the quasi-differences and then ran the quasi-difference regression. And so the multiplier, I think it's smaller than it was before, isn't it? Let's see. Yeah, it was 0.5745 before, and now it's fallen all the way down to 0.1180 rounded. And then this displays the impact multiplier, and the long run multiplier is 0.4611 for this problem. Okay, on to problem 3. So now we want to iterate this. So what we're going to do is generate values of rho again and again until the absolute value of the difference in rho between one step and another is less than 0.001. So the first thing we need to do then is to get our second estimate of rho. We've got a rho 0, now we need a rho 1. To do that, we're going to take this quasi-difference regression from step 2. Remember, we got our initial estimates of beta from this regression here, and those were consistent, but they weren't efficient. We then use those estimates of the residuals from this to quasi-difference, to get rho and then quasi-difference, and then we got new estimates of beta. We can use those new estimates, those new beta hats, to generate new values of the errors. We had one value of the errors up here from this regression. Now we've got another regression. And so we can just generate, maybe I should have called this U hat 1 since it's the other ones were, it doesn't matter. I call this U hat 0. We can generate our second estimate of the U hats, the estimated errors, by taking the regression minus the constant. Now remember I said earlier that the constant in this quasi-different regression is beta 0 times 1 minus rho. So if I divide that by 1 minus rho, I'll isolate beta 0. So this gives me beta 0 minus beta 1 from up here times PCE minus our new beta 2 from here times the lag of PCE, and so on. And so what this gives us here, this generate command, is a new value of the estimated errors based upon these new rows, new betas, sorry, we got from this regression, from the quasi-difference regression. Okay, now we just take those errors and get a new estimate of rho by regressing u hat on its lag, just like we did before. That gives us rho 1. And then I look at the difference as the absolute value of the difference between rho 1 and rho 0. These errors are going to get smaller and smaller. If I did rho 0 minus rho 1, I wouldn't need the absolute value, but I did it this way. So this will give us the difference in the errors. And so if you look here, here's problem 3 with the comments. We generate the new u hat right here. Regress u hat on its lag. This is our new value of rho, 0.954, which prints out down here. And then the difference is 0.032, and that's bigger than that 0.001, so we need to keep going. And so based upon this new rho, rho 1, I can quasi-difference again. These are new estimates of the quasi-differences. Before we used rho 0, now we're using rho 1. We can run a new quasi-difference regression. And then we can use that to get new values of the errors, what I called u hat 1 here, wages minus beta 0 hat minus beta 1 hat PCE minus beta 2 hat times the lag and so on. Finally, minus beta 7 hat times PCE lag 6 times. And we can use this new estimate of the errors to get a new value of rho, rho 2, and then look at the difference here, display the difference. And so if you look at that, here's the new quasi-difference regression. Oh, that was the one we were just looking at, sorry. Oh, no, that's right. And then down here, here's the new value of rho, rho 2. Oops, I went too far. We were only on rho 1, I believe. So here's the new value of rho, 0.9594, and the difference is 0.032. And then we keep doing this procedure. The next difference is 0.0048. Well, that's not far enough, so now I need to generate a rho 3. And so rho 2, so now we just do the procedure again. I've got a new rho, rho 2. I can get new quasi-differences based upon rho 2. That gives me a new quasi-difference regression, a new value of u hat based upon that regression, and then I can use the u hat 2 on its lag to get rho 3. And then we can look to see if we're close enough yet. So we look at rho 3. We see it's 0.9649, and the difference is 0.0006 in absolute value, which is less than 0.001. So this would be my final estimate of rho right here, because now I can stop because the difference is less than 0.001. And up here would be my final estimates of the multiplier. So the impact multiplier would be 0.09946 rounded. And so that's what you do. And so it's just a matter of taking what you did in problem 2 and iterating. And so you just do the same procedure over and over again. Now, if you keep going, you can stop when it's less than 0.001. In your problem, it'll take more iterations than it did here. But if I keep going, that difference will just keep getting smaller and smaller, 0.00062. The next time, it's even smaller, 4 zeros and a 7. And then the estimates are going to basically converge. This one's getting really close. It's e to the minus 0.06. And then finally, it gets so small that it just calls them the same. So this estimate of rho 7 is 0.9649458. And the next one's going to be really close to that. 964945514 with a difference e to the minus 0.08, and then it doesn't change after that. I actually did several more of these, and after that, it still changes way out here somewhere in the decimal, but to the degree of accuracy the program reports, it doesn't change again. So it eventually just converges to some value. But again, you can stop when it gets smaller than minus, smaller than 0.001, the difference in the two rows. So again, in this problem, you'll be regressing real GDP on 5 lags of the federal funds rate. So you'll read the data in, change the sample period, set this so it matches the sample period I asked for in the problem. First, assume exogeneity, and that allows you to just run OLS with robust errors, and then look at the multipliers. For problem 2, for strict exogeneity, we can use a more efficient estimation procedure, GLS, and there's 2 ways to do it. There's a one-step method, which we outlined, and then there's an iterative procedure that's outlined here. And so essentially, for you to do this, you really only have to get the sample period right, change the names of the variables. Instead of wages, it'll be real GDP. Instead of PCE, it'll be FF. This will be RGDP for wages. Change those everywhere. Get the lags right. You'll only have 5 lags instead of 6, and so fix all the commands for that. And other than that, the program should run fairly smoothly, I hope. So that's it.